We have a good number to start. Valdelina, are we? All right, welcome everybody to the virtual seminar of the International Institute of Physics. And this is the last regular seminar of the season. And it is an exceptional pleasure to have with us today Michael Berry from the University of Bristol. Michael is an old friend of the Institute, but by tradition, I make a small introduction. Michael received his PhD from the University of St. Andrews, and he spent all of his career as a professor at the University of Bristol. So he works in.
You did not say that he got his undergraduate degree from the University of Exeter, which I represent.
Oh, hello, thank you, Misha. Indeed. So his undergraduate degree he received from the University of Exeter. But okay, continuing my introduction, Michael is working with different problems in quantum mechanics, optics, complex system, chaos in particular. But probably it is correct to say that in general, Michael is passionate about the beauty of mathematics, and he's trying to find this beauty hidden in different physical problems. So one example that we well know is the connection between quantum physics, topology, and geometry, which is now tightly connected with Michael's name. He's also a great speaker, so he is well known for his outreach talks. For his achievements, he received many prizes and awards from different countries, from international physical societies, and the list is too long to spell here. What is important to us that he is also a member of the International Advisory Board of the Institute, and on behalf of the Institute, I would like to thank Michael for his support to the Institute during all these years. So Michael will talk about the Divergent series and where to find them. So without further ado, I pass the word to Michael. Thank you very much for accepting our invitation.
I'll share my screen, yes.
Please.
Let me say share. And play. Good. Well, thank you for the invitation. And I'm especially pleased to speak that's in the virtual sense of IIP, because it's an organization which I have considerable affection. I think you do very well. You work under difficult circumstances nationally, but nevertheless, you're a very high achieving and successful institute. So it's a pleasure. Now, let me see. It is not working. Oh, now where is my... Oh, yes. Good. So I'm talking today about a tool, a mathematical tool that most physicists, certainly theorists, know a little about, but mostly people don't know all about. I shall speak about that. And there's a history that goes back. Now, let me start. Infinite series, they're the basis for a wide class of approximations in mathematics and physics. We all know we have a series, you start with some guess, approximation, you improve it, you improve it, you improve it. And series are one of the tools. Now, most series in physics are divergent. You learn at school about convergent series, but actually they are rare for reasons to be discussed. Now divergent series is the deepest area of asymptotics, and asymptotics is a study of limits. And limits in physics are usually singular, and what I mean by that is that if you have some limit where some quantity becomes small and you correct it, it's usually not just a simple power series. There's more, at the very least exponentials multiplying, and so the function that you're approximating is non-analytic in the small parameter that you're choosing. Right. Now, and this is very general because singular limits lie at the very heart of relations between physical theories at different levels. Going into that in detail is a different talk, but I'll just make the point now. And understanding divergence has been a thread running through mathematics for several centuries. and the subject has been repeatedly reborn more deeply each time, and it's happening again now. So let's go back to 1747. Here's Thomas Bayes. We know about Bayes' theorem in statistics to do with conditional probabilities, but this is something else. And it's a paper he submitted in 1747, but it wasn't published till 1763, after he died. And this is how you submitted a paper in those days to Philosophical Transactions of the Royal Society. And this is an extract from the printed version. It's the same, actually. If the following observations do not seem to you to be too minute, I would esteem it a favour if you would please to communicate them to the Royal Society. And what he did was to express his bewilderment that a series used by mathematicians, the sum of logarithms of integers up to z, equal to log plus something, is divergent. It doesn't make sense. He says it's a good approximation, but if you really take it seriously, he wrote, if you really take it seriously, the whole series can never properly express any quantity at all, because after the fifth term, we'll see that in a minute, the coefficients begin to increase, and they afterwards increase at a greater rate than what can be compensated by the increase in the powers of z, though z represent a number ever so large. So what's he talking about? He was realizing that Stirling's series for the factorial, here it is, logarithm of the factorial minus the leading term, which is a series, here it is, now we write it with zeta function, it didn't then, but it doesn't matter. And here it is, diverges factorially. It starts by converging, especially if z is large, these denominators, but it diverges factorially. So here's an example, z equals 3. Here are the terms, they get smaller and smaller, looks good, and then the series, the terms diverge. And even factorial 1, that's where it starts to diverge off the fifth term, which is what he had in mind. Now, he was puzzled by this, and he couldn't understand that it could make any sense at all. But Euler, who wrote much deeper work on divergent series in between the submission of Bayes' paper and its publication, he took divergent series seriously. He wasn't worried about them. He said, well, they're coded representations of functions, and that's the modern view. It wasn't always, as we'll see in a minute. Indeed, we'll see now, our bill, divergent series are the invention of the devil. It's shameful to base on them any demonstration whatsoever. Well, he was wrong, but he made the point. And of course, there's silly jokes that people make, like this apocryphal graffito on a wall in the bathroom in Princeton, 2 + 2 = 5 for sufficiently large values of 2. There's a long history of silly jokes of that kind. But the next serious development in our story was Airy, Astronomer Royal, and he was interested in interference fringes that you could see in a rainbow under favourable conditions. Here we are, you see these, you don't always see them. I mean, it depends on whether there's decoherence or not. The raindrops need to be all the same size. He wanted to understand these, which Thomas Young had earlier pointed out as examples of his wave theory of light, illustrations, not just the double slit. Now, it is important to explain natural phenomena. I spend quite a bit of my time doing that, phenomena which every human being has seen, but which somehow the theories haven't been completely and consistently understood. But he realized he was doing something fundamental, really deep, which we would understand now, because he was understanding wave physics near the singularities of ray physics, of geometrical optics. So it's really the bridge between one area of physics and one theory and a deeper theory. Now, these singularities are caustics, they're focal manifolds, which I'll discuss a little bit later. Now, here's the rainbow crossing variable, and Airy realized that the intensity is what we now call the airy function. Actually, intensity is a square, so they call it the squarey function, if you like. This is an integral which, with a slight deformation of the contours, converges perfectly well. And it's a function of this rainbow crossing variable z. And nowadays you can just call it up on in most software. Now, he was frustrated because he wanted to explain these fringes, but he could only calculate this function in this rather small region, which if you square it, you see 2 of the fringes, but 30 had been observed, and you couldn't compare with observation unless he could calculate his functions. He was frustrated. He used a clever numerical method, but it wasn't clever enough. Now, 10 years later, numerics. 10 years later, it was Stokes who made a crucial advance by realizing that what you need is asymptotics, large distance on the bright side, large distance on the dark side. And he found these beautiful expressions, approximations. On the dark side, there's an exponential decay. On the bright side, there's interference with a phase. Actually, now you can think of it as an early geometric phase if you want to. This he understood. Now, he understood a lot more. He understood that these are the first terms of infinite series. So let's look on the dark side. Here you've got this exponential, and for a reason, I'm choosing this quantity f as minus z to the 3/2. There's a reason you'll see later. It's a series, and it's factorially divergent once again. And the least term is the term where the order is equal to this quantity f, which is why I've chosen it. So here you go to the least term. This is for about f equals 16, and indeed it's the 16th term. Z is 5.2 or something. Now, just in passing, in obtaining these formulas, he pre-invented what we call WKB for Z greater than 1. He realized that airy's function satisfied the differential equation. And for Z much less on the bright side, he pre-invented what we call the method of stationary phase. I mean, really ought to be better acknowledged. Okay, now he was actually deeply puzzled by what he had found. And this is a mark of his genius, because most of us would be really happy just to find those formulas, especially in 1847. See, on the bright side, there's a cosine. The cosine is 2 exponentials. Here, E1 and E2, call it. On the dark side, you've just got 1. So these exponentials, here they are. Remember, f is negative. It's confusing, but there's a reason on the dark side. So this exponential is not there, but it is there once you get to the bright side. So he was very puzzled. How can this be? You have a single function, but 2 exponentials. The continuation of one of them is on the other side, but what about the second one? He realized that it appears if you go behind the rainbow in the complex plane. And it appears when you cross a certain line, we now name it after him, and the significance of that line, 1 exponential becoming 2, is that on that line, this f, which is negative when you start down here, is positive, so its contribution is very large, and the one that's going to appear, E2, is exponentially small. So he understood, and I'll tell you later how he understood, that E2 is born when it's maximally dominated by E1. And he was so puzzled and surprised by this that he did some numerical calculations, which I will now repeat. He tested it. So he looked at, first of all, here. And here's the exact value, and here's the series of 1 exponential. It's 6-digit accuracy. Now you go to the other side. Look, you've got the exact, but then you've got this series by itself, which only gives you 3-digit accuracy. But if you add in the small second exponential, there it is. If you add it in, here we are. So if you add it in, you then get 6-digit accuracy. So great. So he showed that it really is true that this small exponential appears. And when I say the series, I mean the asymptotic series for this leading exponential truncated at its smallest term, which is the best you can do naively. And it's that when you correct it, the second exponential appears and you see it clearly in the computation. Really an epic computation for those days. Now, this is the quietly beating heart of asymptotics, this phenomenon. It's a sudden appearance of a small exponential while it's hidden behind a large one when you go from dark to bright behind the rainbow without passing through the origin. And it goes throughout asymptotics in integrals, differential equations, integral equations, difference equations, also near more general types of caustic. I'll talk a little bit about that now. You see, here are some caustics made in optics. This is the fold caustics, and here's the airy function. But also you have other singularities. I'll show you just this one, the cusp, that has its wave function. It's the Pearcey function, x and y, two variables. And this is the singularity, x and y is the same as you and me, excuse me. And here's the wave intensity, you can calculate it numerically. And it too has a Stokes phenomenon. You see, what I told you about the airy functions in the complex plane. And here you have two complex waves, here, two real waves, one complex wave on this side, and you get the exponential appearing as you cross here, also as you cross here. This is the Stokes set. But for higher diffraction catastrophes, and there's a whole hierarchy of them coming from singularity theory, the Stokes phenomenon can occur for real parameters. So here's the cusp. Now here's the bifurcation set, as it's called. That's the caustic. That's what you see dramatically. You give one real and one complex, and here you have three real when you cross the caustic. Here, this is the Stokes set. One real and one complex. One of them disappears, and you just have one real. You hardly notice this in numerical computation. You certainly don't see it with your eyes because it's something exponentially small. But it appears as you cross, and then it grows and becomes important on the bright side of the cusp diffraction catastrophe. Just to point out, in 3 dimensions, you can have 3 kinds of singularity, and these coloured surfaces represent the Stokes sets in the 3 real variables. This grey patterns, these are the caustics that you see dramatically in optical experiments, but the Stokes sets are there. This is with Christopher Howells. Now, there are 2 contrasting phenomena that I've described here. And you've got exponents, I, phi are phases that appear in the corresponding contributions, the dominant exponentials. There's the bifurcation, the caustic, the catastrophe set, where real saddle points collide with each other. So 2, for example, they don't have to be real, but usually they are. 2 real waves collide, and you're left with one evanescent wave. That's going from the bright side to the dark side. The condition for that is that not only is the phase stationary, that determines the rays, but it's stationary to higher order. More generally, it's the Hessian determinant. Now, contrasting with this is the Stokes set, where you have a dominant wave and nothing else, and then a small exponential appears when it's hidden. And the condition for that is that the 2 phases are equal, which means that their imaginary parts are maximally disparate, and the imaginary parts of the phases give you the real exponentials, which the intensities differ enormously. So that's these 2 phenomena worth drawing attention to. Now, Stokes's argument was the following. It was a clever argument, but we think differently now. He thought that if you stop at the least term, you can't do any better. That's an irremovable vagueness. And he showed that that irremovable vagueness is of the same size as the small exponential. And so it's the only place that small exponential can appear without inconsistency is where the dominant exponential with its series has this vagueness. It only happens very close to a Stokes line. Well, we think differently now. We don't think there's an irremovable vagueness. I will explain. The modern understanding is that the second exponential is born from the resum tail of the divergent series of the main exponential, and this happens according to a universal mechanism. I emphasize it's not just the airy function, it's universal. Now, this natural large variable is the difference between the 2 exponents. More generally, it's the difference between pairs of them. We'll see that later. Okay, and this difference between the exponents is of the order, or is integer part, of the order of the least term. So that's why this variable is natural. Now, asymptotics is when f is large. And you can say, here's a series, formal divergent series, and you truncate it just near the least term, and then you've got the tail. So you've got the head and the tail is to be understood. Okay. Now, the asymptotics of the asymptotics is where not only is f large, but n is large. You look at high orders. And there's universal behavior of the high orders, and that was really understood with the greatest clarity by Robert Dingle. He was my PhD supervisor in St Andrews, although I didn't work on this when I was there, and I didn't appreciate it till some years later, based on ideas from Darboux. Here they are. The idea is that the tail, the terms in the tail are universally of a factorial divided by a power, and the power is of this quantity f. It can be, depending on circumstances, this alpha can be a fraction which is different from case to case. It's not important today. Now, this is a huge simplification, because if you've ever done any computations for non-trivial cases in asymptotics and calculated the series, you find that the terms rapidly get enormously complicated. So here's from Dingle's book. Here's a simplest case, a saddle point integral, and you've got some limit, and you go through a saddle point, and here's the dominant contribution. Here are the correction terms. These are derivatives of f and g, and he at the saddle point, and here's the eighth one. Okay. By the way, I've checked this with computer algebra. You can check this. Dingle in the 60s worked everything out using a hand-cranked calculator, and all these integers and so on came out of his hand. I could hear him in his office cranking away on his hand machine, because now you can write a program in Mathematica and you spew out these numbers. Now, the phenomenon underlying this universality, the fact that all of this is like factorial 8 divided by f to the 8, is the fact that high derivatives behave universally. Most asymptotics, all asymptotics that I know, in a sense, local expansions. And so all the corrections are higher and higher derivatives of something. WKB, it's of the potential near to a turning point, but there are many, many examples. This has a lot of physical implication just by itself. I'm just pausing in the story. I mean, I encountered this, first of all, realizing the depth of what Dingle had done, when soon after geometric phases, the way I derived it were adiabatic approximations, and it was the lowest or second lowest order of slowness gave the geometric phase, which had the property, it was independent of slowness, but then there are these higher terms, higher corrections, and I calculated, and I realized that these higher terms could all be expressed as derivatives of something. It's another story to go into details, and I found that there's a universal attractor of high differentiation. Not only do you get the factorial divergence, but because this f is generally complex, as functions of anything, these high derivatives usually oscillate, and I put it dramatically, the universal attractor of the differentiation operator is cos x. It's not widely known, although I've written about it in detail since then. And that's actually been applied. It was, the universal behavior was applied to people looking at electron tunneling statistics. The statistics were the moments which are the derivatives of a generating function. So derivatives appear there as well, and some of the formulae that you get for this universal behavior actually applied directly and enabled the clarification of some experimental data looking at high order correlation functions, high order moments, excuse me. But I want to go further. We've had the asymptotics, large f. We had the asymptotics of the asymptotics, large n. But the final step in this part of the talk is the asymptotics of the asymptotics of the asymptotics, which is this. You've got to resum the tail, and the way you do that is you use Borel summation. Borel summation, you simply replace the factorial by its integral and change the order of integration and summation. Now, the crucial thing is that you want to understand what this does as you cross a Stokes line. So look in the F plane, you cross the real axis, that's when this exponential appears. And the asymptotics is the behavior of this sum, Borel summed, in the region where traditionally we say the series is not Borel summable. Well, it is. It's just a confusion that to say that it isn't. So you ignore all the prohibitions and you do it, and then you get a nice result, which I'll talk about. This small exponential is born not suddenly. It can't be. We're talking about a smooth function. If you go deeply enough, everything has to be smooth, but according to a universal scaling in terms of an error function. And I'll show you it for the airy. If you take the airy function, scale it up a bit, and subtract off the dominant series to its least term, well, that's something big and something big, but you subtract, you get something small, but you multiply again by something big, you get something of order 1, and here's what you get. 1/2 plus the error function of this variable sigma. What is it? It's the imaginary part of f divided by the square root of the real part. Now this represents the thickness of the transition region. It's a universal scaling law, and here is crossing the Stokes line. So negative values, the earth is -1, so it's 0, goes from 0 to 1. And you can test that out with numerics. It's not very difficult. So crossing here from 0 to pi, and here you cross. Actually, I do it from 90 to pi. And here you can see for different values, here's f equals 3, here's f equals 10, and you've got the exact, and you've got this asymptotic theory, which I show you here. Now, of course, what this predicts is that this tail is actually real. It's not quite real, but it gets better and better, and this imaginary part decreases. For this example, the disparity between the two exponentials is about 20,000. And here you've got this tiny little hidden away change of order 1. It's the error function in the airy function. This occurs throughout special functions, Bessel, hypergeometric, gamma. Even the error function itself has its error function, it has its Stokes line. Integrals with coalescing saddles, much more later, and even the Riemann zeta function. Many applications in physics of this Stokes phenomenon. I'm going to describe just one. I won't go through, but I want to describe quantum transitions. I'll spend a little bit of time on this before going deeper into the theory. Now, this is actually the first application I made of this Stokes smoothing when I discovered it. It's about quantum jumps, not the philosophy of why it is that, not measurement theory, but if you consider a quantum transition between two states driven by a slowly changing Hamiltonian, okay, then you want to understand how this happens. Now you have a quantum state with two components, each of which has amplitudes that evolve according to the usual exponential. Here we are, I integral of the instantaneous energy of the Hamiltonian if it were frozen, right, which of course is time dependent if the Hamiltonian is changing. And the system starts out in one of these eigenstates, and adiabatically, there's a theorem, if you go slowly enough, the slower you go, the smaller the transitions are from this instantaneously evolving eigenstate. And that's represented by the component with the dominant exponential. And the subdominant exponential represents the component that's jumped to the other state. Now, it was known and used by atomic physicists and chemists for years, that at the end of the process, after infinite time, when the Hamiltonian is constant again, the probability that you'll be in the new state is beyond all orders of slowness epsilon. It's e to the -1. This is a well-known result. But I asked a different question. How is this accumulated? It starts out at 0, at -infinity, and it ends up exponentially small. Well, the transition happens when the time, its real time, crosses a Stokes line in the complex time plane, which originates from a complex time degeneracy. You see, you assume that the instantaneous states are well separated in real time, but in a complex plane they needn't be. And indeed, it was known that the origin of this small exponential is indeed this degeneracy, but people had not looked at the time development of it as you cross the Stokes line, which crosses the real axis. Okay. Now the details, now here's a crucial point, depend very sensitively on the basis in which you measure the components of the state. You see, by default, you say, let's represent them in the instantaneous eigenstates of the Hamiltonian. But these are just the first terms of a superadiabatic series in WKB theory, which involves the time development of the Hamiltonian. So you've got a WKB series, you can truncate it successively at integers k, starting with instantaneous eigenstates, but then you could do better and better and better. And each time you do that, you could take those two improved states as a basis for monitoring the evolving state. And I'm going to show you pictures of the transition amplitude as functions of time for different values of k. I'm going to show you for two different Hamiltonians that are slow. It doesn't matter what they are. If you know Landau, Zehner, Majorana, that's one of them, and then there's another one. Doesn't matter. In both cases, I've chosen epsilon such that the transition probability at the end is a square of 0.0055. Doesn't matter. Good. Represent the state as coefficients multiplying the instantaneous eigenfunctions. Well, you start out at 0, end up exponentially small, but in between you get to something much bigger, about the square root of epsilon. Still small compared with 1, but all kinds of complex behavior, and these are the two Hamiltonians. It's obviously something universal. All right, well now instead of that, let's represent the state in terms of the first corrected set of states. Well, already you've got much smaller. Instead of 0.08, you've got 0.01. You're taming the transition. And 2, 3, 4, 5. This is the least term. And now you see the error function. There's a little bit of wiggling that has an exponent. It doesn't matter about it. It will get smaller if I'd chosen a smaller exponential. If you go beyond, things start to go bad again. So this is optimal truncation, and it's an example of this phenomenon that I described, that the small exponential, in this case physically, it's the other state, appears. By the way, I just want to make a comment that the predominant series that you're using as a basis has to diverge, because if it converged, it would tell you that you would end up in the same state that you started. Very exceptional cases do that, which would mean there are no transitions. Now, a little bit grandiose and philosophical. What are these transitions? They represent things that happen in the world. I mean, eigenstates are things, and transitions are happenings. So this is the first bud of time-dependent quantum mechanics, the first bud of dynamics that comes from statics. If the series didn't diverge, if that were common, nothing would ever happen in the world. There would be no transitions. So, you know, you can think quite a lot about this. Now, this sensitivity to basis I've just shown you has other applications. It's not something I'll talk about today, but I'll just mention it. If you send a beam of polarized light through a twisted crystal that has loss or gain, so you get big or small exponentials, there are states where you get extreme sensitivity. Even after one twist, you get states that start out on the Poincare sphere representing polarizations 0.02 of a radian apart, tiny, very close, which have completely different evolutions. And it's this sensitivity of evolving the small exponential, all of which you can understand using this asymptotic. I call it the exquisite sensitivity of polarization. Good. Now, we want to go deeper. Traditionally in mathematics, asymptotic series were defined using a prescription of Poincare. You sum to a fixed order. Now, I think this was a very rare mistake that Poincare made. You know, he was a genius, I mean, one of the greatest mathematicians ever. But there are two bad things about this stopping at a fixed order. First of all, you can't capture exponentially small terms because they're beyond all orders. And more important, you don't distinguish between divergent and convergent series. From is just one. Now, that's asymptotics. We call superasymptotics summing to the least term. That's what Stokes did and extended to smoothing of the Stokes discontinuity and the resummation afterwards. you capture the small exponential. What Martin Kruskel calls asymptotics beyond all orders, because the smallest term is indeed, as Stokes realized, exponentially small. It's comparable to the exponential whose appearance we now understand. Hyperasymptotics, which is Christopher Howell's, that's repeated resummation based on the deepest principle in this subject, which is now called the principle of resurgence. It was discovered by Dingle in the 1960s and rediscovered by Ekal in the 1980s within a much more general framework. Here's Dingle and here's Ekal. Okay, two great scientists. And based on this, series don't diverge for no reason. And the divergence must reflect the cause. What is the cause? Well, there are a number of different exponentials representing the same function. Now, if you take any one of them, you've got a formally exact representation of the function, but it diverges. It has to diverge in order to accommodate the other exponentials that you know are there. And moreover, each component series must contain, coded into its high orders, information about all the other exponentials and all the terms of the series that multiply them. You can think of it all as a consequence of analyticity. It's a very deep and beautiful thing. So I'll show you the simplest case that Dingle wrote explicitly. You've got two exponentials, e to the plus or minus a half f. F is the disparity between the two exponents. And you've got a series of sum over coefficients. The large coefficients are, well, I've already told you the leading order behavior is factorial n, in this particular case, -1. It's from WKB or saddle point integration, but it can be different from 1, times the smallest, the leading order coefficient. But then there are corrections gently decreasing in inverse powers of n, which involve the lower terms of the series. A1, A2, A3 all appear in AN. So this is the simplest case of resurgence relation. You can check it numerically. For the airy case, it works beautifully. As I say, Dingle found this in the 1960s. It was rediscovered several times afterwards. Now, hyperasymptotics for this sum as a series of series is the following. You start with the primitive asymptotic, just A0. You know, for many years, I was proud to call myself a first terms man, okay? In that I thought if you approximate the first term cleverly enough, and it needn't always be just a simple exponential, you can get very accurate representations of functions. But that's only the beginning, as I now realize. Well, you sum that to the least term, that's superasymptotics, and then you get an integral representation for the remainder. I'll show it in a while. And then you get an asymptotic series for that remainder, and you sum it to its least term. Well, that's another series tacked on, exponentially smaller. And then you get an asymptotic with a new remainder, and you truncate that, and so on you go. A series of repeated resummations, getting exponentially better. It doesn't converge, but you get much better than just stopping at the least term. And I'll illustrate that. For the airy function, here's airy function of f equals 16, and here's how the terms go. You see, this is the usual asymptotic series, the 0 stage down to about 10 to the minus 8 or so, and that's superasymptotic if you stop there. Crude asymptotics, you should just stop here, the leading order. Well, then you have the first stage, the second stage, the third stage. The series gets shorter, but now you've got down to 10 to the minus 18 or so. So you've done very well, the optimal. Actually, in some large class of cases, instead of getting e to the minus f, you get e to the minus 2 root 2 times f is basically what you get when this procedure stops. By the way, if you don't stop at the least term, if you allow some increase, then with your corrections, you can have as arbitrary accuracy. I don't like that. For many of these functions, you've got convergent series, but they're terribly inefficient, like a convergent series for e to the x when x is large. So although that's an important understanding, actually it was in our paper, we prefer to have continued improvement rather than getting worse before you get better. You know, it's what we did this in the era of Margaret Thatcher, and we called to her philosophy, you live now, but you pay later. And you don't pay much, actually, just as e to the minus 2 root 2. Now, here's the general theory. I'll speak a little bit about that, the general theory. Integrals with a number of different saddles. Okay, well, these are one-dimensional integrals. And this is the complex plane of the integrand with some saddles. Now, there's an extensive theory, which I won't speak about, if you have multiple integrals, but the ideas are similar. So you're interested in the basic saddle, here it is, and through which your integration path goes. Okay. Now, in hyperasymptotics, the corrections involve saddles which are adjacent, and that's a topological criterion. It's the following. You've got a large parameter, has a large modulus, but it also has a phase. And as you change the phase, the descent paths, steep descent paths vary, and you will occasionally hit other saddles. When you do that, and it's a Stokes phenomenon then, those are the adjacent saddles. Then there are other ones which are not adjacent, but they are reached when you go to higher orders. So you can think of this as a kind of multiple scattering theory. I'll show you it in a minute. I'll just show you some formulas to show you just how beautiful this is. You're interested in the nth saddle, and here's the integral through it, which depends on the phase of your large parameter. We're considering rather general cases here. Right, now this is a sum of, this is you can tidy it up by getting rid of the main behavior. And then this has a series. It's a usual asymptotic formal expansion, and the 0th term just involves the curvature of your function at the saddle and also this multiplier. Very good. Well, the exact resurgence formula for the tail is this. This function series is it series to not necessarily the least term, to any term, but you actually take it to the least, the series would be better, as a sum over all the saddles are adjacent to n of something. There's some little bit of topology as an index plus 0 or 1 times an integral which involves all these t's for the other saddles, and it involves these quantities that Dingle called them the singulants, the difference between the exponents. I mean, he didn't have this general formula, but he essentially understood it. And it's an integral over these functions. Now, if you iterate this, which you can do, that's hyperasymptotics, and you get a formal resurgence relation for the high coefficients in terms of the low coefficients of all the adjacent saddles. And here they are. So here you've got the lowest order, the next order, the next order, involving, again, these singulants of the high orders of one series involve the low orders of all the other relevant series. Okay, there's the early terms. Now, iteration gives you this hyper series, and so basically what you get, whenever you terminate, you get one of these integrals. So you get series and series and series, more and more saddles, and there involves these universal S-fold hyperterminant integrals, which you have to calculate, but they're then the same for all functions. And I'll show you how this works. Oh, typically, I just slip through. Each series is about half the length of the previous one. Now, I'll show you again this Pearcey integral. I've chosen two values, one of them is complex, and you've got 3 saddles. Right, here they are. And I'm talking about the path through this saddle number 2. So hyperasymptotics generates a sequence of series. You can think of them as scatterings between the saddles. I just want to show you how it goes. So here we are. This is superasymptotics for saddle number 2. And then one scattering, you go from 2 to 1 or 2 to 3. They're both adjacent as it happens. And these give you these terms of the series. 2 scatterings. You get from 2 to 1 to 2, or 2 to 3 to 2, back to 2, and then you can go on. And so that's superasymptotics and these different paths. And you get at each stage, not very difficult to calculate contribution. I want to make a comment. it would have been very hard to do this without computers and software. And it's a general theme. It's another lecture that I give, how just as we tell our politicians that all new science that we do has a potential of leading to new technology, well, new technology also leads to new science. And you couldn't do this mathematics without computers and without computer algebra. Just not possible. So there's a synchrony, in a cultural synchrony in these developments. Well, let's have a look. I mean, the lowest order, that's hyperasymptotics. Sorry, no, it's just the very lowest order. You get an error of about 1% fractional error. You go to superasymptotics, that's here, and you get down to 10 to the minus 6 fractional error. You go to hyperasymptotics when you stop, and you've got 10 to the minus 12, that's pretty good. And of course, here's the exact, which you should compare everything. So that's mostly what I wanted to tell you. So yes, I'm just showing you how that you get increasing accuracy. Now, that's some little just remarks to end with. I want to celebrate 3 people who are no longer with us. There's Dingle, asymptotics triangle of people. Dingle, who understood resurgent resummation. I think his was the deepest contribution. Special functions, asymptotics of, and who quickly caught on to these new developments, was Frank Olver, and then Martin Kruskal, asymptotics, many different areas of physical mathematics and applied mathematics, including, he coined the term asymptotics beyond all orders. He came to it from nonlinear theories in plasma physics, and which he was working on in the 1950s. He came to realize there are certain exponentially small phenomena, and he coined this. He also invented surreal numbers. No, he didn't invent, sorry, that was John Conway. He thought surreal numbers would be a mechanism for rigorously expressing asymptotics. That hasn't been actually successful, but he was a brilliant scientist. Just a curious thing. There's a strange connection between some of these asymptotics and southeast London. I can't resist telling you that. You see, Airy was the Astronomer Royal in Greenwich in South London. Frank Olver was from Croydon, that's a district of South London. Pearcey, the Pearcey function, was in Woolwich, which again is in South London. And my student and now a colleague in Southampton on much of the work I've described was Christopher Howells, and he was born and grew up in Greenwich. I'm not part of this club because I'm from north of the river in Ilford. Okay, so to summarise, what's the legacy from Euler, from Dingle, et al.? Well, it all came from Stokes' insistence on understanding how the rainbow's dark side is connected to the interference fringes on its bright side. The Stokes phenomenon, of course, that's the basis of the heart of everything that I've described. He insisted on understanding how these two exponentials, how one exponential becomes 2. There's a letter, part of a 55-page letter that hasn't survived, that he wrote to his fiancée about this. He wrote something like this: I've been doing what I guess you won't let me do once we're married, spending the whole night trying to understand a mathematical problem. Recently, I struggled to understand something about an integral that Airy had discovered, and it took me 2 or 3 days of hard fighting, and finally I understood it. And that was Stokes. The rest of the letter hasn't survived. It's a very intimate, private letter, which we don't know what it said. A divergent series is not meaningless. It's not a nuisance. It's an essential and informative coded representation of a function. And in the 1990s and the 2000s, much new mathematics has originated from Resurgence. And I list here a number of people. It's not just our work, major interesting developments. And there's a literature being applied now in quantum field theory and in string theory. I haven't followed those applications, but there's a literature, and the basic ideas are the same. You've got Stokes phenomenon, you've got resurgence, but there are additional features that come when you have more than one-dimensional integrals, and in particular when you have path integrals that are infinite dimensional. So that's current. These are current developments, and I've written myself a number of papers on these matters. They're all on my homepage. You can just download them if you are interested. So thank you very much for your attention, and I would welcome any questions or comments if people have them. So again, thank you for your hospitality today.
Thank you very much, Michael, for this beautiful talk, and we can indeed pass to questions.
I'll unshare my screen. Here we are. Somewhere.
Let us please raise your hand or write your question in the chat. Let's see.
Lots of good afternoons.
Let me start maybe with a question, and my question is about the universality. So you said that
yes.
So what does the universality mean in this case? So how you so does it mean that for all function in the vicinity of the Stokes line we have this universal form of the series that you wrote?
No, it's much more than that. I mean, that's an application of the general idea, but it's a nice application. It goes back to Stokes and explains what he discovered. But no, it's much more general. I mean, it's the universality of the factorial power type of divergence. Of course, there are mathematical divergences can be of any kind. I mean, we all know what's celebrated in the literature, especially recently, is 1 + 2 + 3 + 4 + 5 is -1/12, this Riemann-Zeta regularization. So there are lots of, and Euler was a master at understanding not exactly that one, but 1 - 1 + 1 - 1 - 1 + 1 so equals a half. I mean, all kinds of other forms of, but commonly in physics, the universality class is one of a factorial divided by a power. And the reason for that goes back to Darboux. And it's because if you wonder, it's to do with the fact that asymptotics involves higher and higher derivatives. And what Darboux showed is that if you have a function on, say, on the real axis, and you want the derivative somewhere, higher and higher, higher, eventually it's dominated by the nearest singularity in the complex plane. And if that singularity is a pole or a branch point, its high derivatives automatically bring factorials and powers. So that's really the heart of it. And it's very, very general. I mean, I've looked at it, written about this in great detail, this universality of high derivatives, in particular, how the contribution, as I mentioned, can involve oscillations because the exponential needn't be real. That's what I said, the universal attractor of high derivatives is like cos x, but more generally, it's this factorial divided by a power that's the basis of all of this universality. So that's the class. Yeah. So underlying in physics now, underlying this is a theory which may or may not be complete, like some of the field theories. It might not be axiomatically expressed. For example, there might not be an exact integral, convergent existing integral, like in some of the cases I described. So somewhere or other, there's some analyticity involved. Okay, so that's the universality.
Okay, thank you. I have another question, which is about this hyperasymptotics, and it's, as you mentioned, it was also clear from the pictures that the number of terms in each time in series expansion is lower. So does it mean that it will be a finite process?
Yes, it is. It's a finite. Now we've worked very hard. Chris Howells and other people too, and myself with other people, to try to find convergent representation of the same type. Now, there are other convergent representations. I mentioned if you, many of these functions have convergent series. I mean, the airy function has a convergent series. It's useless. It's like e to the x when x is 1,000, trying to compute that. Also, even within asymptotics, if you don't stop at the least term, but you allow terms to increase, and then you apply research, then you can get arbitrary accuracy. What I would like will be a scheme that continually improves and overcomes this e to the -2 log 2 I mentioned, that seems to stop us at the moment. I haven't found that. I don't know if that's fundamental or if it's curable or dealable with, but so that's the situation anyway. But still, I mean, to calculate, for example, the first zero of the Bessel function to 1 part in 10 to the 18, when you're supposed to be using a theory for asymptotically large zeros, is okay. I mean, it's not. We're pleased with it, but it's not the end, you know. Yeah.
There was a comment in the chat from Mauricio Dominguez that
oh, great!
mentioned that they're using this for in this resurgence and it's kind of series in infinite range Hubbard model.
Oh, excellent! Oh, good. I don't know about that application, but good. And I hope it's Mauricio. Here, I see you there in the chat. I hope it's useful.
So he actually asked another question, if you know about any applications to electronic systems. I know Mauricio. Okay. Oh, Mauricio can ask his question himself, actually.
Yes.
I can.
Hello. Yes.
Hello. We are struggling with this series, Divergent series, that appear in the Hubbard model with infinite range interaction. It's very clear. They have all these properties that you described. At the 5th power, we have good agreement with what we expect, and then things diverge. And we have been trying to use Borel and so all these methods that have been used, for instance, by Saint-Justin.
Oh, yes. Oh, indeed.
So I think
what's the large parameter?
One. I mean, I want to stop in one, but of course, one is.
No, I mean physically, what's the large parameter?
Z is the range I am starting is from 0 to 1.
Okay.
So at 1, it seems that everything diverges. So 1 plus epsilon, I can be alive. And then I'm starting the divergent series that appear.
Is powers of epsilon.
1, yes.
Okay, good.
As the Hubbard model is, we have been studying this model for in main occasions, in main circumstances. We came to this point that the divergent series is in the heart of the solution for thermodynamics at high temperatures, for instance. Seems to appear very clearly.
Very
so
good.
Thank you very much.
Yes, no, its comment is interesting because you ask about electron systems. I can say 2 things about that. The first, I did mention what surprised me, that the people who are looking at the statistics of electron tunneling in quantum dots, they measure the electrons and they measure the very high moments, the large fluctuations. And of course, high moments are high derivatives of a generating function, and they find exactly these factorial power business that and these universal oscillations, because they have a parameter which they can vary, and they see precisely these universal oscillations of the high derivatives there. But more important, Dingle started out as what was then called a solid-state physicist in the 1950s, and he realized that in order to understand some of the properties of de Haas-Van Alphen resonances and other things and properties of electrons in magnetic fields, he needed asymptotics of, for example, of Fermi-Dirac functions, more refined than what was in the literature at the time. And he is actually very well known. There's a Dingle temperature, there's Dingle-Holstein resonance, other things. But once he realized that he could understand the necessary asymptotics much more deeply, he moved over into asymptotics for the last half of his life and made these brilliant contributions that I mentioned. So there's a history that comes from electronic systems.
Yes. The interesting point also that I'd like to make a remark is that the statistics that govern our particle, let's say. It's the Haldane statistic. It's a fraction statistic.
Yes, okay.
So it makes things interesting because I don't see anybody.
Yes, thank you. I didn't know this connection. Thank you. Yes.
I also noticed that in the picture of Dingle that you showed us, there was a book on his desk called Solids, right?
The principles, actually, coincidentally, I think that was the book. Soon after I came to Bristol, my colleague here, the head of department, although we never worked together, was John Simon, who wrote that book. So that was Dingle in his slightly later life, yes.
Okay, we have one more question from Fabio Ribeiro. Fabio, please.
Thank you, Dmitry, for the word. Michael, thank you for this amazing and historical talk, right? Look, when you showed the change from the bright side with two oscillating exponential to the dark side with one evanescent exponential, I would like to know if it makes sense to think there is a kind of phase transition between these two regimes.
I would express it this way. The answer is, first of all, you can think of this. As they're called, of which the airy function is the simplest. The PSC is the next one with the cusp I showed you. They all obey certain scaling laws, which are powers at the singularity itself, different powers of the wave number, the K. And you can think of these as critical exponents. So it's now, it isn't, I mean, there was, in the beginning, when this was discovered, people thought, oh, this will explain critical exponents in critical phenomena. It doesn't. It doesn't explain them. It's the analog of Landau theory, which is kind of mean field theory. And the reason why critical phenomena are more subtle is that you have infinite degrees of freedom and different things happen. You have renormalization and so on. So there are connections, but with the diffraction industries, where they are deep is in a different sense. I mean, the functions themselves are very interesting. They describe interferences that you can see. But you can, yes, you can think of them in a sense as describing phase transitions. So thank you for that. Yeah.
No, I thank you for this good answer, clear answer. So if I can think in a phase transition, do you have in mind what would be the universality class?
Oh yeah, mean field theory. But mean field theory is not trivial when you go to high orders and different and different more complicated phases. So that's the analog. And in optics, we do see these higher singularities. So what would be mean field theory not so interesting in condensed matter is interesting and indeed deep in optics. You know, there are experiments exploring the details of these higher functions whose significance is that they're universal. That's the point. In that universal means stable under perturbation. Yeah.
Right. Thank you for these clear answers. Bye. All the best for you.
Thank you very much, Fabio. Do we have other questions? I don't see.
I had two questions. One was historical.
Yes.
Could you say a bit about what Borel and Poincaré were interested in when you talked about Borel's summability and Poincaré asymptotic?
But Borel I don't know. I just know his formula. But Poincaré was very interested in asymptotic, and he knew about small exponentials, but for some reason, which I don't know, is in his definition of an asymptotic series, he sort of forgot it. I mean, it's a curious thing. He certainly was aware of small exponentials. I mean, many of the phenomena he described, now we now think of as KM theory, tori in chaos theory and chaotic zones in between, which he understood in a certain sense without having the theorems. I mean, he knew about exponentially small phenomena, but so I can't tell you. I mean, it's a psychological question about somebody who was very interested himself in the psychology of mathematics. He wrote a lot about it.
Right.
So I don't know. And with Borel, I just know his summation, but I don't know I'm embarrassed not to know the context in which Borel summation was discovered. Maybe it was prompted by Poincaré. I don't know. It's about the same time.
I see.
Yeah. So I'm sorry I can't give a satisfactory answer.
Not at all. Yeah. So my second question was, you said you've explained it twice, so I'm asking for a third explanation, third time.
Yes.
About your comment that really grabbed me about the universal attractor of the differentiation is cosine.
Yes.
Can you break this down as simply as possible?
I can. I mean, it's a theorem. If you take any function analytic in a strip, including the real axis, and you ask about its high derivatives, well, they either vanish if it's a polynomial, but if it's not a polynomial, then with a wide range of different implementations I'll describe in a minute, locally, this high derivative behaves like cos x. Now, of course, cos x times a factorial, cos x with some scaling, cos x which is with a sin x, I mean cos x with a phase, of course, but still the heart of it is that. And this comes from the fact that you get contributions from the nearest singularity. Now, sometimes there are no singularities, you've got an entire function. Then, if you represent, this is how you derive, you represent the derivative as a Cauchy integral around the point, you know, little integral of the function around the point. Then you expand until you hit a singularity. But if you don't hit any singularities, you will then hit saddle points, and then they contribute in slightly different scaling. So it's looking at the asymptotics of that integral and how you encounter interesting points in the function, either saddle points or singularities. And in the paper I eventually wrote, I had a number of examples. The simplest one is in my original paper in 1987 on corrections to geometric phases, and I understood it was a general phenomenon. And then you find that in the complex plane, you can see that it's, you know, geometric phase is to do with loops, is to do with circuits, and the successive corrections correspond to successively smaller circuits, and often it's around the north pole of the Bloch sphere. But as you go higher and higher, these circuits wind more and more times where they get smaller, but then they get bigger again. And the geometry is Maclaurin's I can't remember, Maclaurin's universe, I can't remember the term, spiral of 1718. That's the function. Well, I didn't write any more. I understood it. It was in the paper. But then a number of years later, there was a paper by Doyne-Farmer, which came to a slightly similar conclusion. And he was interested in random matrix theory. In random matrix theory, you've got the characteristic polynomial of an infinite dimensional, characteristic function of an infinite dimensional matrix whose zeros are the eigenvalues. And then he said, well, what happens if you take the derivative? What are the zeros then? He found that the zeros get more and more regularly spaced away from random matrix theory as you differentiate more and more times. And that's a special case. In the end, you'd get cos x. It'd be like a system with a regular spectrum. So I then went back and I wrote a much more detailed paper and gave a number of examples of different functions where, surprisingly, you see this same phenomenon. You can see it numerically as well as analytically if you differentiate. I'll give you a really simple example. Take a Gaussian, right? You know that the derivatives of the Hermite functions times Gaussians, Hermite polynomials times Gaussians. Now, if you take any point, eventually the region between, you get two turning points, and as you differentiate more and more, you get higher and higher order harmonic oscillator functions, where the turns are farther and farther apart. In between, they oscillate, and eventually any point you choose will lie within the region between the two turning points, and you'll get locally it's like cos x. So this is just something about, I don't know if that helps.
It helps a lot. Thank you for these remarks. What was the paper, the second paper you said after?
Oh, it's in, if you look on my homepage, I think it's 2007 or so, or 2005, Universal Oscillations of High Derivatives, something like that.
Great.
I think that the University of Track, it should be in all textbooks. I mean, it's such a simple thing. Universally, all functions become like cos x. It isn't, of course. So,
as yet.
Well, it's 20 years now. Yeah. Yeah.
But thank you so much. Thanks.
Good.
Thank you, Tushar. Do we have more questions? I see Misha turned on his microphone. Maybe he wants to ask a question.
I mean, we know similar things as an exponential integral. Everything is factorially higher.
Of course, that was the first.
And in error function, and I think I teach it even in methods module at Exeter now.
Yeah,
and we came across using exponential integral for some kind of famous Loudon problem, actually, because it has quasi-exact solutions where it can be used.
Well, first of all, hello neighbor, because you're quite close if you're in Exeter now. But yes, I mean,
I haven't seen you for a long time.
That's exactly, but I'm not very far away. But the exponential integral was one of the examples I gave. My very first in my paper on the Stokes smoothing in 1989. Of course, that's the simplest, almost the simplest example of this general phenomenon of the Stokes phenomenon, and you can illustrate the smoothing if you look in the complex plane. So yes, and as I mentioned in the talk, I didn't write exponential integral, but you see it in Bessel functions, hypergeometric error function. Even the error function itself has an error function hidden in it, inside itself, as well as just all these diffraction and catastrophe. So yes, it's universal means universal. Yeah.
By the way, I've seen Kostya Hanin a couple of weeks ago in Nice.
See?
Kostya Hanin, you remember we met in Bristol?
Of course I do, yes.
He's now in Europe for a while.
Well, just please, I have to correct you. We are in Europe.
We aren't.
We are in Europe. You can't change geography. So of course, I know you mean continental Europe. And I just make a comment that it was in Nice, visiting Frederick Pham in 1988, that I discovered this universal error function smoothing. I thought while I was there, I should think about something that might interest him, because he had worked on asymptotics of different types. And so it was actually there in Nice, in the wonderful old building in the Parc Valrose. Were you there, or were you in this horrible Sophia Antipolis?
We mostly, I don't know, we were wherever he took us.
Yes. Good. Anyway.
Yeah.
So Nice, I have a great affection for Nice for that reason. Yeah.
He's in the observatory, actually.
Oh, okay, different again. That's another. That also has a very distinguished history. Yeah. Beautiful.
He's permanently in Toronto, but he's on leave, on sabbatical now.
Very good. Very good. Yes.
All right. So I think we can now close this seminar. And thank you very much again, Michael, for giving this beautiful talk. And as I mentioned, this is the last seminar of the season, the last regular seminar at least. And I would like to thank everybody who participated. I would like to thank our technical support people, Valdelino, Giuliano, for being with us and making all this experience smooth, nice, and also Tiago, who is a co-organizer of this seminar. So he did a great job organizing this seminar. Thank you very much, especially participants that showed their interest and they were coming, and they, in this way they supported us. So I hope to see you again next season, preferably offline than online, and have a nice end of the year and Happy New Year.
Thanks to all of you. Bye-bye.
Bye.
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 Bye-bye. All the best. It was a great pleasure to watch your seminars.
Thank you, Fabio,
Thank you.
for your contribution.
Recording stopped.